Welcome to this explainer. Today, we're doing something really exciting. We are going to translate the absolute mind-bending reality of the quantum realm into simple, everyday concepts. If you've ever felt completely overwhelmed by the physics of quantum computing, you are in exactly the right place. We're going to break it all down using scenarios you already know and understand.
All right, let's just jump right in with a question that sounds, well, totally impossible. It perfectly frames the whole mystery of quantum computing. Imagine you're flipping a coin. While it's spinning through the air in a total blur, is it heads or is it tails? Classical logic tells us it has to be one or the other, eventually, right? But the quantum world challenges that very foundation. That spinning coin perfectly captures the fundamental difference between the phone in your pocket right now and the incoming quantum revolution. Our normal computers operate on a strict either-or basis, kind of like a coin that has already landed on the table. But quantum computers operate using qubits, which act way more like that spinning coin. They exist as both heads and tails simultaneously right up until you finally stop it to take a look.
So let's start with part 1, classical ones and zeros, and how normal computers work.
Underneath all the flashy apps and sleek software, our everyday computers rely on these tiny little hardware components called transistors. And these transistors really just do one simple thing. They detect whether electricity is flowing or not. If there's a voltage, let's say 5 volts, the computer reads that as an up state, or a 1. If there's 0 voltage, it reads a 0. That is the fundamental building block of literally all our current digital technology.
And here's the crazy part. Everything you see on your screen, from text messages to complex 4K videos, is just a massive, lightning-fast combination of these binary ones and zeros. If you want the number 215, it's just a binary sequence. The letter A, the computer translates that into the number 65 and then into binary. A specific shade of green, it's a combination of red, green, and blue values mapped from 0 to 255, all in binary. Even the video you are streaming right now is just millions of these binary calculations updating sequential images pixel by pixel.
We also use this exact same classical logic for probability. Take an online store, for example. If 10% of viewers add an item to their cart and 50% of those actually buy it, it's a simple linear calculation to find your total sales probability. It's 5%. It's straightforward and it's highly predictable.
Which brings us to part 2, the double-slit mystery and subatomic behavior.
Okay, picture this famous physics experiment. Scientists set up a barrier with 2 tiny slits and fired individual light particles, known as photons, right through it. Now, if photons act like little physical bullets, you would expect them to go straight through the slits and form 2 simple lines on the wall behind them. But that is not what happened at all. Instead, they formed a complex, spreading interference pattern. This blew physicists' minds because it proved that a single photon was somehow acting like a wave, going through both slits at the exact same time and actually interfering with itself.
Now here is where things get genuinely mind-bending. Enter the observer effect. When physicists put a measuring device right at the slits just to see which slit the photon actually went through, the photons seemed to somehow know it was being watched. The complex interference pattern instantly disappeared and it was replaced by 2 simple lines. The photon acted like a regular particle again. But if you unplug the measuring device, the interference pattern instantly returns. Just observing the system fundamentally changed its reality by collapsing the wave function.
If your head is spinning right now, honestly, don't worry. As the legendary physicist Richard Feynman famously noted, if you think you understand quantum physics, you don't. Being confused is literally the correct reaction to how strangely our universe behaves at the subatomic level. Let's move on to section 3, superposition and being in both states at once.
To wrap our heads around this, let's talk about physicist Erwin Schrödinger's wildly famous thought experiment. Picture a cat placed in a closed box. Inside this box is a radioactive substance that has an exact 50-50 chance of decaying and releasing a poison. Because the box is sealed shut, we have absolutely no way of observing what's going on inside.
According to the rules of quantum mechanics, right up until the exact moment you open that box to check, the cat is in a state of superposition. It isn't just maybe alive or maybe dead. Mathematically speaking, it is both alive and dead at the exact same time. It's only the act of opening the box, the measurement itself, that forces reality to collapse into one single definite state.
So bringing this back to quantum computing, we represent this idea using a qubit. Think about the spin of an electron. A classical bit is either distinctly spin up, which is a 1, or spin down, which is a 0. But a qubit in superposition isn't just a strict 1 or 0, it exists as a complex probability vector. It points both up and down simultaneously, right until the exact moment we measure it.
All right, Section 4, entanglement and some seriously spooky action.
To understand entanglement without getting bogged down in all the heavy math, let's use a very simple analogy. Imagine we have one apple and one banana. We place them into two separate, identical closed boxes. Now, we send one box on a rocket ship far out into space, and we keep the other box right here on Earth.
Now say you open your box here on Earth. You look inside and you find the apple. Instantly, without a single second passing, you absolutely know for a fact that the box floating out in space holds the banana. You don't have to fly into space, open it, and measure it. The state of the space box is immediately determined the very second you observe the Earth box.
This is a perfect everyday illustration of entanglement. In the quantum world, two qubits can become perfectly correlated like this. They are linked in such a way that measuring one instantly collapses the wave function of the other, forcing it into a corresponding state. And the wildest part of all of this happens instantaneously, even if the two entangled qubits are separated by millions of light years.
This instant connection? It completely shatters classical physics. Nothing is supposed to travel faster than the speed of light, yet this correlation happens with zero delay. This bothered Albert Einstein so much that he skeptically called entanglement spooky action at a distance. Yet time and time again, repeated experiments have proven that this spooky action is very, very real.
Finally, Section 5, the quantum advantage and faster computation.
Okay, let's think back to those classical bits we talked about earlier. If you string together 8 regular computer bits, which makes one standard byte, they can store exactly one number between 0 and 255 at any given moment. It could be 14, it could be 200, but it is strictly just one single number at a time.
But quantum computers, they play by a totally different rulebook. Thanks to superposition and entanglement, a sequence of just 8 qubits doesn't hold one number. It represents a probability vector of all 256 possible numbers simultaneously. It holds 0 and 1 and 2, all the way up to 255, all at the exact same time.
Think of it like a giant maze. A classical computer acts like a mouse running down every single dead end one by one until it finds the cheese. But a quantum computer? It floods the entire maze with water all at once. By manipulating the phases of these superpositions, it mathematically cancels out the wrong paths and amplifies the correct one, solving problems in literally seconds that would take traditional computers thousands of years to figure out.
And that leaves us with one incredibly fascinating thought to close out this explainer. If a string of just a few qubits can unlock this mind-bending level of simultaneous calculation power, what currently impossible problems will we solve when we master thousands or even millions of them? From curing diseases by modeling complex molecular interactions instantly, to completely redefining global cybersecurity, the quantum revolution is truly just getting started. Keep that curiosity alive, and thanks so much for exploring this reality with me today.